Good morning, my name is Rich King, and we are in front of Charleston Rigging this morning, and we are doing pull testing on several of the drop stitch fabrics that we have here. We are testing the pin and anchor system that is used to connect the walls and then the walls and the roof together. What we're going to be doing is putting these pieces in tension and finding out what the breaking strength is of this little pin. This pin is what holds all of the different pieces together when the bunkhouse is fully assembled. Second piece that we're going to be testing is the ground strap D-ring. This D-ring is actually pretty important because this is what's going to hold the bunkhouse to the ground. Imagine this is the bunkhouse, this is the strap. You're going to be putting a stake through here, and you're going to put the stake through here into whatever the ground material is. We're going to be testing this in tension, so we're going to be intentionally trying to pull it apart and finding out what the breaking strength is. Last and final piece that we're going to be testing is the upper tie-down D-ring. So this upper tie-down D-ring, we're going to have a hook that comes in through here, and then we're going to have a strap that goes down into another stake that's placed into the ground. We have tested this previously on other types of materials. We got some great results. We had 660 pounds of breaking strength, and then for the small D-ring, and then we had 1,220 pounds of breaking strength on the larger D-ring. This is a drop stitch material, so we're kind of interested in what the differences may be, if any. So stand by. So we're inside Charleston Rigging now, and we've got Virgil here, and Virgil's made this little contraption in order for us to test the pin and anchor system in here. We got a shackle that's placed on one end of the drop stitch pillow here, and then we got this rig, and what we're going to do is attach this to the other end here, and then we're going to pull it apart and find out what the breaking strength of the pin and anchor system is. All right, so we just tested the breaking strength of that pin. We put it into tension, started slowly pulling it apart. We got everything on camera, but this is the pin after the test. We got it up to 595 pounds before it sheared. What's important to note is there was no damage to the PVC anchor at all. That looked great. Test number 2 is complete. We've pulled this thing, we put it in tension. We've got one D-ring that survived, the other D-ring came apart here. You could hear all of the strings of that substrate just pulling and popping. It kind of sounded like a bag of popcorn going off, but this would never occur in real life. In any event, we got 587 pounds of pressure before that D-ring failed. One other thing to note, the structure itself is still inflated. It is still retaining air. That is a great weld on this little pillow piece. Test number 3 is complete. We tested the ground strap that's holding the bunkhouse to the ground. We got it up to 607 pounds before the stitching broke apart from the actual pillow. Again, the pillow has not lost any air, the welds are still complete, but there's the failure. All right, so pretty good day of testing here. Charleston Rigging took the 3 pieces in there and found out what the breaking strengths were going to be on the 3 different pillows that we had tested. We tested the ground strap D-ring, we tested the side D-ring, and then we also tested the pin and anchor system. So we're going to take all of this data back to our shop and go over the wind simulation data that we had already gathered and just make sure everything is up to snuff. All right, so we're back at the shop. I'm standing in front of the first prototype that we have here. We developed that one several months ago, and we took a look at how those pillows performed in tension. We started pulling them apart, saw the strings start breaking, but one of the things that was neat to notice was how well the seals around the edges of that pillow did. One of the things that got us curious was, well, if they performed that well under tension, what is it going to look like under compression? We don't have professional compression testing equipment here at the shop, so what we decided to do is gather a couple things that we had laying around here and see how much weight we could actually put on top of this pillow, and see if the seals were going to hold up then. Inside of the PVC, we actually have a layer of nylon strings. You can see all the little dimples that are part of the pillow itself. Those strings help provide shape to the pillow and give it its added strength. Once we inflate the system to about 3.5 psi, it becomes very rigid. It's very hard for it to move. One of the things we need to test is how much pressure can we actually apply to this pillow itself. We've devised this little contraption back behind us, and we're going to test it out. All right, pretty successful test, I must say. We tried testing it 2 different methods. One was the trailer method, where we put the wheel of the trailer on there and we loaded up as many people as we could find relatively quickly. We put about 1,805 pounds worth of human on top of that little trailer. Now that weight spread out amongst 2 wheels, so we can't get an exact measurement of how much weight was on there, but we surmised it's somewhere between 1,200 and 1,500 pounds. Next test we did was with the Toyota 4Runner. We brought it out there, we tried it with the rear wheel first. It held without a problem, and then we went to the front wheel. Once we had the front wheel put on there, we surmised it's about 1,500 pounds. The base weight of that vehicle is about 4,500 to 4,800 pounds. So 1,500 pounds is probably what we're looking at underneath this structure. As you can see, it performed flawlessly. It's still hard. The tire tracks are there as proof. I think it was a pretty successful test. All right, we're back inside. We've taken a look at what the drop stitch material would do in tension. We've taken a look at how it performs in compression, and then we also understand the braking strength of the D-ring, the pins, and then the ground strap. So the final piece of all of this is taking a look at the wind data and making sure that the wind data matches what we expected in terms of the braking strengths. All right, so in order to determine what the wind forces on the house were going to be, we created a 3D model of the bunkhouse. What we wanted to figure out was whether or not the roof was going to survive a 65-mile-per-hour wind. When the wind hits the structure itself, a moment is going to be created and try to pull the roof up off of the wall section. We know that there are several anchors in place. We know what the braking strength of those anchors were, but we didn't necessarily know what the moment was going to be on those anchors. So we ran the wind simulation and we got all of the numbers, and we've determined we have a sufficient number of anchors in place in order to hold the roof down. So let's take a look at the numbers themselves. What we found out was that the shear force of that 65-mile-per-hour wind was going to be the strongest force for which we needed to prepare for. Those numbers are located here. When the wind hits the side of the structure, there is a pressure number, there is a friction number, and then you add those 2 together and you get the total number. For a 65-mile-an-hour wind hit dead center along that broad wall, we came up with 496.5 kilograms or 1,094 pounds. We have 4 ground straps in place, each with a 600-pound braking strength. In addition to that, we have 4 upper tie-down D-rings in place with an additional 600 pounds. So we have 4,800 pounds worth of anchoring force against a 1,094 pound wind shear force. That means that we have 4.8 times the anchoring capacity from what the wind is going to be. The bottom line is that you have to make sure that the tent is anchored properly in order to exceed that 1,094 pound load placed on the structure by the 65-mile-per-hour wind. You can do that through staking and making sure it is anchored properly, and or the use of plates and placing a vehicle on top of the plates. Just to show some of the shape of the wind as it comes across the structure itself, these were some pressure clouds that were developed. This diagram represents the flow of the wind across the structure once the wind has hit the broadside of the wall. And here is a velocity diagram of what the wind looks like as it comes across the structure. The wind comes in from the left, it hits the broadside of the structure, goes up underneath the eave, and then crosses the roof line. These lines represent the velocity of the wind as it goes across the top of the building. What we wanted to do was make sure that the data that we received from the tension tests, the compression tests, and the braking strength of the D-rings, the ground straps, and the pin and anchor system matched or exceeded what the wind requirements were from the model data that we had received previously. In conclusion, what we found was that the shear force from the 65-mile-per-hour wind was the greatest force on the bunkhouse itself. We have 4.8 times the anchoring capacity on the bunkhouse from what the 65-mile-per-hour wind was going to produce, as well as 3.4 times the anchoring capacity of what the moment was on the roof line. So rest assured, we have a very firm and stiff structure that's going to withstand a 65-mile-per-hour wind, provided it is anchored properly.